4.2 light-years away, a rocky planet circles a dim red star. We call it Proxima Centauri B. It might have water, it might have air. And our fastest spacecraft, screaming through the void right now, would still need over 70,000 years to get there. Tonight, you board the mission. We will face fuel that doesn't exist, sails torn by single grains of dust, crews that age while Earth forgets them, and a star that flares hot enough to sterilize its own neighbour. If you want the real numbers behind interstellar travel, hit subscribe and stay with us. Strap in, we launch now. Picture a dim red star, smaller and cooler than the bright one we orbit. Now picture a rocky planet hugging that star so tightly its year lasts only 11 Earth days. That planet is Proxima Centauri B. And on paper, it sounds like a second Earth waiting for us. The numbers seem promising at first. Its mass sits at roughly 1.17 times that of our home world. It orbits inside what astronomers call the habitable zone, the thin band where liquid water could exist on the surface. Its host star is the closest star to ours, sitting about 4.2 light-years out in the constellation Centaurus. As confirmed by European Southern Observatory observations in 2016, the planet is real and its mass is measured. So far, this sounds like the obvious destination for humanity's first interstellar mission. Then you read the fine print. Proxima Centauri is a red dwarf, and red dwarfs throw tantrums. The star unleashes massive flares without warning, sometimes brightening by thousands of times in seconds. A flare that big, hitting a planet that close, would strip an atmosphere down to bare rock over millions of years. Whether Proxima B still has air at all is currently an open question. Scientists are split. Some models suggest the atmosphere survived, others suggest the planet is now a cold, airless ball. That uncertainty matters more than you might think. Because to even ask whether Proxima B is habitable, we need to get something there to look. A telescope from Earth can spot the planet's pull on its star, but it cannot tell us if rain falls there, or if oceans exist, or if the surface is shielded from radiation. The only way to know is to send a probe, and here is where the mission planner's job turns into a nightmare. The planet is the closest exoplanet ever found. Yet closest in interstellar terms is a cruel word. Light, the fastest thing in the universe, takes more than 4 years to make the trip. The fastest object humans have ever built, the Parker Solar Probe, moves at roughly 430,000 miles per hour at its closest approach to its star. Even at that speed, the journey to Proxima would still eat up more than 6,000 years. A single human lifetime cannot survive that gap. Civilizations cannot reliably plan that far ahead. Every empire we know about has fallen in less time. The planet is also tidally locked. One side faces the star forever, baking under permanent daylight. The other side faces eternal night, frozen solid. The only place a human could possibly stand is a narrow ring of perpetual twilight stretching around the boundary. That ring might host windstorms strong enough to flatten anything we built. So we have a target. We have a planet. We even have the coordinates dialed in. What we do not have is any working way to send a crew there and have them arrive alive. This is the puzzle every chapter of this mission briefing will pull apart. The propulsion, the shielding, the food, the mines, the politics. Every system has to work for centuries, and every one has a known failure point. Before we touch the engineering, we need to understand the distance itself. Because 4 light-years sounds short, the reality is something else entirely. A light-year is a measurement that hides its own size. The phrase sounds almost casual. 4.2 of them stand between us and Proxima. People hear light-year and picture a long road trip. The truth crushes that picture instantly. 1 light-year equals roughly 5,800,000,000,000 miles. Stretch that out for a moment. If you drove a car at 70 miles per hour without stopping, with no traffic and no fuel breaks, covering 1 light-year would take over 9 million years. The dinosaurs went extinct 66 million years ago. A car leaving Earth back then, driving constantly, would still be working on its 7th light year right now. Proxima Centauri B sits 4.2 of those distances away. The numbers feel abstract until you build a model. Shrink our home star down to the size of a basketball and place it in New York City. On that same scale, Earth becomes a peppercorn about 80 feet away. Jupiter, the giant of our system, is a marble 400 feet down the street. Pluto sits more than half a mile out. Now find Proxima Centauri on that same scale. It would be in California, roughly 2,000 miles from your basketball. This is the trap. Our solar system feels enormous because we evolved on a planet that takes a year to circle its star. Yet the entire span from our world to the edge of Pluto's orbit is a rounding error compared to the gap between any two stars. The distance from Earth to Pluto is about 3.7 billion miles at the far point. The distance to Proxima Centauri is more than 6,000 times farther. The fastest spacecraft ever launched toward interstellar space is Voyager 1, currently coasting at around 38,000 miles per hour. Voyager has been flying for 48 years. It has covered a distance of about 15 billion miles. That is roughly 23 light hours. Light makes that same trip in less than a day. Voyager will reach the rough distance of Proxima in about 73,500 years. And Voyager isn't even aimed at Proxima. The probe is heading in a different direction entirely. If we wanted to redirect a craft like Voyager toward Proxima today, the journey would still take more than 70,000 years at that speed. 70,000 years ago, modern humans had only just started painting on cave walls. Agriculture would not exist for another 60,000 years. The pyramids were 65,000 years away from being built. Asking a machine or a crew to survive that long with no resupply is an engineering problem unlike any other. Every joint, every wire, every seal, every molecule of food has to last. Every system that breaks must be repairable. Every spare part must be carried or made on board. This is why mission planners keep coming back to one brutal conclusion. The answer is not to fly faster on chemical rockets. Chemical rockets simply cannot do this job. The math forbids it. Voyager set the record using gravity assists from giant planets. Even with that boost, the speed barely budged on cosmic scales. Something fundamental has to change about how we push spacecraft, or we will never leave our own backyard. The first thing to understand is exactly why our most famous probe falls so short. In 1977, 2 spacecraft left Earth with a job no human had ever attempted. Voyager 1 and Voyager 2 were built to study the outer giants and then keep going, forever. Nobody on the launch team expected the probes to last past the 1980s. Almost 5 decades later, both are still calling home. Voyager 1 is currently the most distant human-made object in existence. As of recent NASA tracking, the probe sits more than 15 billion miles from Earth, deep in interstellar space. Its radio signal, travelling at light speed, takes over 23 hours to reach mission control. When engineers send a command, they wait nearly 2 days for the answer. The probe carries a golden record, a message in pictures and sounds designed to introduce humanity to anyone who finds it. The record was a romantic gesture, a bottle thrown into the cosmic ocean. The team behind it knew the odds of recovery were essentially zero. Why so hopeless? Run the math. Voyager 1 travels at about 38,000 miles per hour relative to our star. That sounds blistering. A bullet from a high-powered rifle moves at roughly 2,000 miles per hour. Voyager is 19 times faster than a bullet, hour after hour, year after year. At that speed, the probe will reach the equivalent distance of Proxima Centauri in about 73,500 years. Pause on that figure. Recorded human history goes back about 5,000 years. Voyager would need to fly 14 times longer than all of recorded history to cover 4 light years. And again, Voyager isn't aimed at Proxima at all. The probe will pass within 1.6 light-years of a different star, called Gliese 445, in about 40,000 years. The closest pass to any star happens by luck, not design. Here is the part that makes mission planners despair. Voyager achieved its speed using a once-in-a-generation alignment of the outer planets. Engineers used the gravity of Jupiter and Saturn as a kind of slingshot. Each flyby flung the probe faster without burning fuel. That alignment was rare. It was something that happens roughly every 175 years. We cannot replicate it on demand. And even with that gift, the probe is still glacially slow on interstellar scales. To reach Proxima in a single human lifetime, say 80 years, a probe would need to travel at roughly 5% of the speed of light. That equals about 33 million miles per hour. Voyager moves at 0.0057% of light speed. To match the lifetime requirement, we would need to multiply Voyager's velocity by roughly 1,000 times. No chemical rocket ever built can do that. Voyager's power source is also dying. The probe runs on plutonium decay, generating less electricity each year. Mission engineers have been shutting down instruments one by one to stretch the remaining juice. By the early 2030s, Voyager will likely fall silent. The craft will keep moving, forever. But nobody on Earth will hear it again. That silence is the verdict on chemical-era propulsion. Our most successful long-distance probe is a heroic failure on the scale this mission demands. The push that lifted it off the launch pad in 1977 was the wrong tool for the job. Understanding why means looking at how rockets actually work, and the answer involves a problem that traps every chemical engine ever built. A rocket is a controlled explosion with a direction. Strip away the engineering glamour, and that is what every chemical rocket does. Fuel and oxidizer mix inside a combustion chamber. They ignite. The hot gas roars out the back at high speed. By Newton's third law, the rocket gets pushed forward. Bigger explosion, faster exhaust, harder push. For 60 years, this design has carried us from the launch pad to low Earth orbit, to the Moon, to Mars. The Saturn V rocket that sent astronauts to the lunar surface stood 363 feet tall and weighed over 6 million pounds at liftoff. Most of that weight was fuel. The actual payload, the part that mattered, was a tiny fraction at the very top. This ratio is the wall. Every chemical rocket has a maximum exhaust speed set by chemistry itself. Burning kerosene with liquid oxygen, the best you can squeeze out is about 10,000 feet per second of exhaust velocity. Burning hydrogen with oxygen pushes that to roughly 14,000 feet per second. These numbers represent the theoretical ceiling. No clever engineering can push past them, because the energy stored in the chemical bonds is finite. To reach Proxima Centauri in a human lifetime, the probe needs to move at 5% of light speed. That equals roughly 49 million feet per second. Compare that to the 14,000 feet per second a hydrogen rocket can manage as exhaust velocity. The shortfall is over 3,000 times. You might think the answer is simple. Just carry more fuel. This is where the trap closes. A rocket equation worked out by Russian scientist Konstantin Tsiolkovsky in 1903 governs everything that flies. The equation has a brutal logic. To go faster, you need more fuel. But more fuel means more weight. More weight means you need even more fuel to push the extra fuel. The relationship grows exponentially, not linearly. To reach just 1% of light speed using a hydrogen rocket, the fuel mass required would be larger than the observable universe. Yes, you read that correctly. The math says the rocket would need more hydrogen than exists in every star, every cloud, every galaxy we can see. This is why chemical propulsion cannot, ever, get us to another star. The wall is absolute. Engineers have tried every trick to stretch chemical performance. Staging, where empty fuel tanks drop away, helps a little. Cryogenic propellants, frozen and dense, help a little. Exotic chemistry like fluorine and lithium burns hotter, but those fuels are also lethally toxic and impossible to handle safely. The result barely budges the equation. Even SpaceX's Starship, the most ambitious rocket currently being built, maxes out at maybe 2% improvement on what the Saturn V did half a century ago. The vehicle is bigger, cheaper, and reusable. The exhaust velocity is essentially the same. This is why mission planners stopped pretending chemical engines could do interstellar work decades ago. The discussion moved on. The serious question became, what kind of physics could replace combustion entirely? The first answer was elegant. Stop trying to throw fuel out the back fast. Throw it out the back smart. A whole new family of engines was born from that single insight, and the leading example sips its propellant like a dieter at a banquet. The strange catch is that going gentle, in space, sometimes wins the race. A rocket carrying its own fuel is hauling its own grave. This is the second curse of chemical propulsion, and it is worse than the first. Imagine a delivery truck that can only run on its own cargo. To deliver a package, the truck has to burn part of itself along the way. The farther it goes, the more it eats. Eventually, the truck runs out and falls silent, possibly before reaching the destination. Every rocket faces this exact problem. The fuel and oxidizer make up most of the launch weight. As the engine burns, the rocket gets lighter. A lighter rocket is easier to push, so the same engine pushes it faster. Engineers love this part. The cruel half follows. To reach a high speed, the rocket needs a lot of fuel. That fuel weighs something. To launch that fuel off the pad, you need still more fuel. To launch the fuel that launches the fuel, you need even more. The pattern compounds. Tsiolkovsky's rocket equation describes this exactly. The math says that to reach 10 times the exhaust velocity of your engine, the rocket must be roughly 2,000 times heavier than its dry mass. That ratio is a death sentence for chemical engines trying to reach interstellar speeds. A real example helps. The Saturn V carried about 6 million pounds of fuel to launch a payload of around 300,000 pounds to the Moon. That is a fuel-to-payload ratio of about 20 to 1. To go 10 times faster than the Saturn V could manage, you would need a ratio measured in millions to 1. The rocket would be larger than a mountain, and most of it would be propellant tanks. So mission planners attacked the equation from the other side. Instead of carrying more fuel, what if the engine itself was more efficient? What if each pound of propellant produced a much bigger push? That single question opened a new doorway in propulsion. Engineers measure engine efficiency using something called specific impulse. Think of it as miles per gallon for rockets. Higher specific impulse means more push per pound of fuel burned. Chemical rockets max out at around 450 seconds of specific impulse. That is the ceiling. Ion engines, a completely different technology, achieve specific impulse values of 3,000 seconds or more. Some experimental designs hit 10,000 seconds. The improvement is staggering. Here is what that means in practice. NASA's Dawn spacecraft, launched in 2007, used ion thrusters to visit 2 different asteroids in the main belt. The probe carried only about 900 pounds of xenon propellant. Yet over its mission, Dawn changed velocity by more than 25,000 miles per hour. A chemical rocket trying to match that performance would have needed dozens of tons of fuel. Dawn did it with the weight of a small car's worth of xenon. The trick is that ion engines throw their exhaust out incredibly fast, faster than any chemical engine could ever manage. The thrust at any moment is tiny. A Dawn-style ion thruster pushes with the force of a piece of paper resting on your hand. That sounds pathetic. In space, with no friction and no gravity to fight, that gentle push runs for months or years. Time multiplies the small force into enormous speed. This shift, from explosive thrust to patient acceleration, became the foundation for every realistic interstellar engine on the drawing board. The first real-world example proves the point with surprising elegance. Imagine a kitchen hose with 2 settings. On the first setting, a fire hose blasts water at full pressure. The flow is huge. the push backward on whoever holds it is brutal. Water disappears from the tank in seconds. On the second setting, the same water passes through a tiny nozzle at incredible speed, but the volume is small. The push is gentle. The tank lasts for hours. This is the difference between chemical and ion propulsion. The chemical engine is the fire hose. The ion drive is the tiny fast nozzle. An ion engine does not burn anything. The trick involves electricity and a noble gas, usually xenon. Inside a chamber, the engine uses electric fields to strip electrons off xenon atoms. That turns each atom into a positively charged particle, called an ion. Strong electric fields then accelerate those ions out the back at speeds approaching 90,000 miles per hour. The reaction pushes the spacecraft forward. The force is tiny. A typical ion thruster produces thrust roughly equal to the weight of a quarter resting in your palm. You could not lift a feather with it on Earth. Trying to launch a rocket off the ground using an ion engine would be like pushing a freight train with a butter knife. In the vacuum of space, that tiny push works miracles. Without atmosphere to fight, without gravity dragging on the craft, every gentle nudge adds up. Run the engine for a year, 2 years, 10 years, and the spacecraft just keeps accelerating. The math stops being about peak thrust and starts being about endurance. NASA proved the concept with a probe called Deep Space One. Launched in 1998, the mission tested ion propulsion as the main engine for the first time. Deep Space One ran its thruster for roughly 16,000 hours over its lifetime. By the end, the craft had changed its velocity by nearly 9,000 miles per hour, all from a fuel load of about 190 pounds of xenon. A chemical rocket trying to do the same job would have needed thousands of pounds of propellant. The Dawn mission took the technology further. Dawn became the first spacecraft to orbit 2 separate worlds. The probe explored the asteroid Vesta, then peeled off, accelerated for years, and arrived at the dwarf planet Ceres. Such a maneuver was impossible with chemical engines. The fuel demands would have been absurd. Ion thrusters made it routine. European, Japanese and Chinese probes have since used similar engines for missions to Mercury, asteroids, and even commercial satellites guarding their orbits. So why hasn't the technology gotten us to Proxima? The catch hides in the numbers. Even running for decades, an ion engine on a probe-sized craft might push the spacecraft up to about 100,000 miles per hour. That sounds enormous. On interstellar scales, the speed is still painfully slow. At 100,000 miles per hour, the trip to Proxima Centauri would take roughly 28,000 years. Better than chemical, but still a death sentence for any crew. The problem with ion drives is power. The engine needs vast amounts of electricity to ionize and accelerate enough particles to push a heavy spacecraft. Solar panels weaken with distance from any star. Nuclear reactors capable of feeding a serious ion engine remain mostly on paper. To go faster, the next propulsion idea got darker, and much louder. In 1958, a team of American physicists drew up a Starship blueprint that would horrify modern engineers and thrill them at the same time. The plan was called Project Orion. The propulsion method was straightforward. Drop atomic bombs out the back of the spacecraft and detonate them. Catch the explosion on a giant steel plate. Ride the shockwave forward. Every 5 seconds. For weeks. Or years. Stanislaw Ulam, one of the original designers of the hydrogen bomb, came up with the idea. Theodore Taylor and Freeman Dyson led the engineering team at General Atomics in San Diego. These were brilliant, sober scientists. They believed Orion would work. The math, terrifyingly, agreed with them. The basic design called for a spacecraft the size of a small city. The pusher plate at the rear would be made of steel hundreds of feet across. Behind that plate, massive shock absorbers like enormous springs would soak up the impact of each detonation. Above the absorbers sat the crew compartment, the cargo holds, the laboratories, the engines for fine maneuvering. A single Orion blast ejected a small atomic bomb from the rear, timed to explode at a precise distance behind the pusher plate. The plasma from the explosion slammed into the plate. The spacecraft jumped forward. The shock absorbers compressed. The pulse settled. The next bomb was already loading. A typical mission profile called for thousands of bombs. Tens of thousands. The performance numbers were staggering. A nuclear pulse Orion could theoretically reach 1/10 the speed of light, depending on the bomb design. That meant a trip to Proxima Centauri in about 45 years. A human crew could conceivably make it within a single lifetime. A team built and tested a small-scale model. In 1959, engineers launched a craft they called Hot Rod, propelled by chemical explosives shaped to mimic the bomb pulse pattern. Hot Rod reached an altitude of about 300 feet and landed safely on its parachute. The proof of concept worked. The full Orion was supposed to follow. It never did. 3 problems killed the project. The first was political. In 1963, the United States and the Soviet Union signed the Limited Test Ban Treaty, which banned nuclear detonations in the atmosphere, in space, or underwater. Orion launched from the ground would violate the treaty thousands of times in a single mission. The second problem was fallout. Even an Orion launching from orbit would scatter radioactive debris across the cosmos. The debris from a ground launch would dump enormous amounts of radioactive contamination into Earth's atmosphere. Calculations from the era suggested every full Orion launch would cause statistically detectable cancer deaths worldwide. The third problem was practical. Building thousands of working nuclear bombs sized exactly for an Orion engine, then storing and timing them perfectly during flight, demanded engineering tolerances that did not exist anywhere. Still don't. Fully. Even today. Project Orion was officially shelved in 1965. The blueprints went into a vault. Some of them are still classified. The idea refused to die. Engineers kept asking whether the underlying physics could work without the radioactive horror show. What if you replaced fission bombs with smaller, cleaner fusion pulses? What if the engine fired tiny pellets of fuel that ignited from a beam of energy? A British team picked up that thread in the 1970s. The result was bigger than the Empire State Building, and it had a name that came straight out of Greek mythology. In 1973, a small group of British engineers and scientists started meeting in London on weekends. They called themselves the British Interplanetary Society. Their goal was to design in detail a real interstellar spacecraft, a working blueprint with every system specified. The project ran for 5 years. The result was a document called Project Daedalus, a 2-stage fusion rocket capable of reaching Barnard's star 6 light-years away in 50 years. The design was monstrous. The completed spacecraft would have measured nearly 200 meters long, roughly the length of 2 football fields stacked end to end. The wet mass at launch would have been around 54,000 metric tons. That equals the weight of 1.5 Empire State Buildings suspended in space, ready to fly. The propulsion system worked on a principle called inertial confinement fusion. A target chamber at the rear of the craft would receive small pellets of fuel, each about the size of a marble. The fuel was a special mix of deuterium and helium-3, 2 isotopes that fuse cleanly when squeezed hard enough. 250 powerful electron beams would slam into each pellet at the same time. The pellet would compress so violently that its core hit the temperatures and pressures inside a star. Fusion ignited. The pellet exploded. The plasma roared out the rear of the spacecraft, pushed by the engine's magnetic field. 250 pellets per second. 250 fusion explosions every second. For years. The first stage of Daedalus would burn for 2 years, accelerating the spacecraft to about 7% of light speed. The first stage would then drop away, spent. The second stage would ignite and continue accelerating for another 1.5 years, pushing the final velocity to roughly 12% of light speed. At that velocity, the spacecraft would coast, engines silent, for 47 years across interstellar space. Daedalus had no plan to slow down at the destination. That detail still surprises people. The Daedalus team made a deliberate choice. They wanted to prove that an interstellar mission was technically possible within 50 years using only physics already understood. Slowing down at the target would have doubled the fuel requirement and pushed the launch mass even higher. The probe would simply blast through the Barnard star system at 12% of light speed, taking pictures and readings during a flyby that lasted only hours. Then it would coast onward into the void forever. The fuel problem nearly killed the design before it began. Helium-3 is incredibly rare on Earth. A few kilograms exist worldwide, mostly from nuclear weapon decay. Daedalus called for 30,000 metric tons of the stuff. The team's solution was bold. Mine the atmosphere of Jupiter. Build a fleet of robotic balloon refineries that would float in Jupiter's clouds for 20 years, sifting helium-3 from the gas giant's hydrogen. That sub-project alone was bigger than any space mission ever attempted. The Daedalus team published their full design in 1978. The British Interplanetary Society stamped it as a feasibility study, not a construction plan. Nobody expected anyone to actually build it. The point was to prove that the math worked, that an interstellar probe was, on paper, an engineering project rather than a fantasy. The follow-up came from an unlikely place. A group of Naval Academy students in Maryland decided to take the idea further and to fix the part Daedalus had ducked. In 1987, a team of cadets and faculty at the United States Naval Academy in Annapolis began working with NASA on a different interstellar concept. They named it Project Longshot. The goal was bold: send a probe to Alpha Centauri, the triple star system that includes Proxima Centauri, and have the probe actually slow down and orbit when it arrived. Daedalus had given up on deceleration. Longshot refused to. The design specifications were dense. The completed spacecraft would weigh around 400 metric tons at departure, much smaller than Daedalus, but still massive by today's standards. The propulsion system used the same basic idea. Pulsed fusion with small fuel pellets ignited rapidly to drive the spacecraft forward. The differences were in the details. Longshot used a much smaller pulse than Daedalus. The fuel was deuterium and helium-3, again, but in different ratios. The ignition came from a powerful onboard laser, not electron beams. Engineers calculated the engine could fire a pulse roughly every second for 100 years. The probe's top speed would reach about 4.5% of light speed. Mission timeline: roughly 100 years one way to Alpha Centauri. Slower than Daedalus. Slower by a lot. The slower speed was the entire point. A spacecraft moving at 12% of light speed cannot stop at its destination using any propulsion system known to physics. The fuel needed to brake from such a velocity would dwarf the spacecraft itself. The Longshot team did the math and accepted a longer trip in exchange for the ability to actually arrive somewhere. To slow the probe at Alpha Centauri, the engine would fire backward for the final 15 years of flight. The fusion drive, originally pointing rear, would rotate to point forward. Pulses would push against the direction of travel, gradually shedding velocity. By the time the spacecraft reached the target system, it would be moving slowly enough to enter orbit around one of the 3 stars in the Alpha Centauri group. Once in orbit, the probe would unpack a science package designed to study the system for decades: telescopes, spectrometers, particle detectors. Communication antennas pointed back at Earth. The whole mission was supposed to last 200 years from launch to data return. Several things stood in the way of building Longshot. The reactor design called for sustained fusion ignition rates that have never been achieved on Earth. Modern fusion experiments, even the most advanced ones, can produce a few seconds of net energy output under controlled conditions. Longshot needed 100 years of continuous, reliable pulse firing in deep space, with no maintenance possible. The communication problem was just as ugly. From Alpha Centauri, the probe would need to beam data back across more than 4 light-years of vacuum. The signal arriving at Earth would be incredibly faint. The receiving array on Earth would need to be larger than anything ever built. The signal would also take over 4 years to travel one way. The cadets knew this. They documented every flaw alongside the proposed solutions. The final report ran to dozens of pages of careful engineering. They submitted it to NASA in 1988 as a study, not a proposal. Longshot, like Daedalus, sat on a shelf. The next attempt to crack the interstellar problem threw out fusion entirely. The new idea was to leave the engine on Earth. Just send the spacecraft, pushed by a beam of light larger than any laser ever built. In April 2016, a Russian billionaire named Yuri Milner stood next to physicist Stephen Hawking at a press conference in New York. Milner announced that he was committing $100 million of his own money to a project called Breakthrough Starshot. The goal sounded almost reckless. Send a fleet of postage stamp-sized spacecraft to Alpha Centauri at 20% of the speed of light. Get there in 20 years. The science board for the project included Hawking, Mark Zuckerberg, and a roster of physicists from MIT, Caltech, and the Russian Academy of Sciences. The team was serious. The math was, to almost everyone's surprise, plausible. The spacecraft itself looked nothing like a traditional probe. Each unit, called a starchip, weighed less than a gram, roughly the weight of 3 paper clips. The chip carried a camera, a power supply, a navigation system, and a communication laser, all squeezed onto a piece of silicon smaller than a thumbnail. Each starchip attached to a sail. The sail was the heart of the design. The sail measured about 13 feet across when fully unfurled. Total weight, less than 1/4 of an ounce. The material had to reflect light almost perfectly while withstanding extreme heat. Engineers proposed exotic materials like graphene, dielectric metamaterials, or aluminum alloys folded into nanoscale structures. The sail had to survive being hit by a beam of light powerful enough to vaporize a regular mirror. The propulsion came from the ground. A laser array planned at roughly 100 gigawatts of total power would sit somewhere in a high desert region, possibly the Atacama in Chile. The array would consist of thousands of individual lasers, each beam combined into a single coherent shot. The beam would target the sail just after launch. For about 10 minutes, the sail would absorb the photon pressure of that beam. Light has no mass, but it carries momentum. A photon hitting a reflective surface bounces off and pushes that surface backward. Stack enough photons together and the push becomes serious. In those 10 minutes, the starship would accelerate from rest to 20% of the speed of light. That equals roughly 134 million miles per hour. The acceleration would peak at around 60,000 times Earth's gravity. Any normal spacecraft would tear itself apart instantly under that kind of stress. The starship survives only because it has almost no mass to be torn. After the laser shuts off, the chip coasts. For 20 years, it screams across interstellar space at 1/5 of light speed. No engine. No fuel. Just inertia and a piece of silicon racing toward another star system. When the chip arrives at Alpha Centauri, it has only a few hours to do its job. The flyby will be too fast to slow down. The camera takes pictures of any planets in the system. The data goes back to Earth via the chip's tiny laser, transmitting toward home. The signal takes another 4.37 years to crawl back across space. Total mission time, launch to data return, about 25 years. If a single chip works, the team plans to send thousands, perhaps tens of thousands. Each one a slightly different mission. Some scout, some image the planets, some test course corrections. The fleet acts like a swarm, redundant by design. The plan is brilliant on paper. The engineering hides a knife edge. A single grain of dust at 1/5 light speed becomes a weapon that could end the entire mission in a flash. A piece of dust the size of a sand particle, sitting still in space, looks harmless. Hit it at 20% of the speed of light, and the picture changes completely. This is the hidden enemy of every fast interstellar mission. Space, even the deepest space between stars, is not empty. The interstellar medium is filled with thin gas, ice crystals, and dust grains. Most of these particles are tiny. A typical interstellar dust grain measures around 1/10 of a micrometer, smaller than a bacterium. Some are bigger. A few reach the size of a small grain of sand. At normal spacecraft speeds, an impact like this is almost meaningless. The grain leaves a microscopic pit in the hull, and the mission continues. At 20% of light speed, physics changes the rules. The kinetic energy of any moving object follows a simple formula. The energy equals 1/2 times mass times velocity squared. The velocity squared part is what makes things terrifying. Double the speed, and the energy goes up by 4 times. Multiply the speed by 1,000,000, and the energy goes up by 1,000,000,000,000. A star chip moving at 20% of the speed of light, hitting a dust grain weighing 1 milligram, releases energy roughly equivalent to a hand grenade detonating against. The spacecraft. The grain itself does not need to be heavy. The speed does all the destructive work. A single such impact would shred a star chip into vapor. The breakthrough Starshot team has run simulations of dust collisions for years. The results are sobering. On a journey of more than 4 light years, the chip will pass through interstellar dust constantly. Most grains are too small to do real damage. Some are not. The team estimates that any individual chip has a meaningful chance of being destroyed by a single bad impact during the flight. Defenses are limited. The chip is too small to carry meaningful armor. Adding mass slows the acceleration during the laser push and makes the whole concept break. The team has proposed orienting the sail edge first during cruise to present the smallest possible cross-section. They have considered coating the sail in a sacrificial layer that vaporizes when hit, absorbing some of the impact energy before it reaches the precious silicon. The strategy that may save the mission is simple in concept. Send a lot of chips. A single grain of dust in the wrong place destroys one star chip. The next chip, 10 seconds behind, follows a slightly different trajectory. The dust cloud at any single point in space is sparse enough that not every chip will hit a deadly particle. If the team launches 20,000 chips, some fraction will survive the trip. Even if only 1 in 100 makes it, that still leaves 200 working spacecraft arriving at Alpha Centauri. The dust threat is currently classified as a known major risk. The number of grains in the path between Earth and Alpha Centauri is itself a topic of ongoing research. Probes from previous missions have measured dust density in the inner solar system reasonably well. Beyond the heliopause, the boundary where our star's solar wind ends, the data thins out. The first probe to map the dust on the route to Alpha Centauri does not yet exist. A heavier mission, one with shielding, might survive the journey. A heavier mission cannot accelerate as fast on a laser sail, so the chips stay tiny and accept the risk. Even if a chip survives the dust gauntlet, a deeper problem is waiting at the destination. Stopping. Going fast in space is a solved problem. Stopping is something else entirely. This is the riddle that has tortured every interstellar mission planner. The same physics that allows a craft to coast through the void at a fraction of light speed, fuel-free, also forbids it from slowing down once it gets there. Without an engine that can fire backward against the direction of motion, the spacecraft simply blasts past its destination at full speed. Breakthrough Starshot accepts this. The starship will streak past the planets of Alpha Centauri at 20% of light speed, recording everything it can in a few hours, then tumble onward into the dark forever. For a probe, that may be acceptable. For a crewed mission, it is a disaster. The problem is brutal mathematics. A spacecraft heading toward Proxima at 5% of light speed carries enormous kinetic energy. To shed that energy, the craft has to push back against its own motion just as hard as it pushed forward to get there. Same fuel, same engine burns, doubled, because deceleration requires its own propellant supply. Daedalus, for example, was designed to brake by mounting a second-stage fusion engine that would fire forward during the final years of flight. Adding that engine more than doubled the spacecraft's launch mass. The cost was staggering. For a chemical rocket, deceleration is impossible. The Tsiolkovsky equation, the same brutal math from earlier, says the spacecraft would need to be larger than the universe to break from interstellar speeds. For a fusion rocket, deceleration is theoretically possible, but eats most of the mission's fuel budget. For a laser sail, deceleration looks impossible at first glance. The laser is back on Earth. The sail is light years away. There is no way to push the sail backward from such a distance. Engineers have proposed clever workarounds. One idea, called magnetic braking, would deploy a giant superconducting loop after the sail crossed most of the distance. The loop would generate a magnetic field hundreds of miles wide. Particles in the interstellar medium, mostly hydrogen and helium nuclei, would slam into that field and bounce off. Each particle would steal a tiny piece of the spacecraft's momentum. The thin gas between stars could theoretically act as a brake. The numbers are punishing. The interstellar medium is thin. A magnetic loop millions of times wider than the spacecraft itself might work. A loop big enough adds mass. Mass slows acceleration. The same trap, dressed up differently. A second idea, proposed by physicist Robert Forward in the 1980s, involved splitting a laser sail in two before arrival. The outer ring of the sail would detach and continue accelerating ahead of the spacecraft. Once ahead, it would reflect the laser beam, still chasing the craft from Earth, back onto the inner sail. The inner sail, now hit by light from the front, would decelerate. The plan was elegant. The plan also required perfect alignment of two sails separated by light years. A tiny mistake at separation would mean the reflective ring drifted off course and missed the inner sail entirely. A few teams continue to study deceleration. None has produced a design that works without massive trade-offs. For now, every honest interstellar mission has to either accept a flyby that ends in seconds or carry a second spacecraft's worth of fuel just for braking. The solution may lie not in engineering, but in the medium between stars. The very gas that has tortured every flyby plan turns out to have one useful property. The space between stars is almost empty. Almost. A typical region of interstellar medium contains roughly 1 atom per cubic centimetre. Compare that to Earth's atmosphere at sea level, which contains around 25,000 million billion atoms per cubic centimetre. The difference is enormous. The interstellar medium is, by any reasonable definition, a vacuum. For a spacecraft moving slowly, the medium is meaningless. The probe slips through and feels nothing. For a spacecraft moving at 5% of light speed, the math flips. At interstellar velocities, even 1 atom per cubic centimetre starts to act like a wind. The spacecraft is ploughing through a sparse gas at enormous speed, sweeping up particles by the trillion every second. Each collision is tiny, but the running total is large. This is the principle behind the magnetic sail, sometimes called a magsail. The concept goes back to 1988, when American physicist Robert Zubrin and engineer Dana Andrews published a paper describing how a spacecraft could use the interstellar medium itself as a brake. The idea? Deploy a giant superconducting wire loop, miles wide. Run a current through the wire. The current generates a powerful magnetic field, hundreds or thousands of miles across. Charged particles in the medium, mostly stripped hydrogen nuclei called protons, hit that field. The field deflects them. Each deflection transfers a tiny amount of momentum from the particle to the spacecraft. The transfer points backward against the direction of motion. A magnetic sail brakes a spacecraft using nothing more than the interstellar wind itself. The advantages are striking. No fuel needed for deceleration. The propellant is already there, scattered through the void. The brake works only because the spacecraft is moving fast. As the craft slows, the braking force drops smoothly. Eventually, the magnetic sail provides almost no force, and the spacecraft can use small chemical or ion thrusters to make final maneuvers. The math works. On paper. The complications are several. First, the sail has to be huge. To produce meaningful braking force, the magnetic field needs to spread across a region millions of times larger than the spacecraft itself. Building a superconducting loop tens or hundreds of miles wide and powering it for decades demands materials and engineering that do not yet exist at scale. Modern superconductors require extreme cold to work. Out in deep interstellar space, the temperature naturally hovers near absolute zero, which helps. The wire itself still has to be light, durable, and capable of carrying enormous current without breaking. Second, the magnetic field interacts with everything, not just braking particles. Cosmic rays passing through the field can damage the spacecraft. Charged dust grains can be redirected in unexpected ways. The crew, if any, sits inside a region of artificial magnetism stronger than anything humans typically experience. Third, the deceleration takes a long time. A magnetic sail does not slam on the brakes. The force is gentle, like the ion drive but in reverse. Slowing a spacecraft from 5% of light speed using a magnetic sail might take 10 or 20 years of continuous braking. The braking phase becomes a significant chunk of the entire mission. Even with all those caveats, the magsail remains the most promising deceleration concept on the table for crewed missions. A few groups continue to refine the design. None has built a working prototype, even on a small scale. The technology waits for someone willing to fund the test article. The next family of engines tried to skip the deceleration question entirely by using a fuel so dense and powerful that the original mass budget shrank to almost nothing. The fuel was matter's mirror image. A gram of antimatter mixed with a gram of normal matter would release more energy than a small nuclear weapon. This is the fundamental promise of antimatter propulsion. The math is breathtaking. Any encounter between a particle and its antiparticle, an electron meeting a positron, a proton meeting an antiproton, ends in complete annihilation. Both particles vanish entirely. Their entire mass converts to pure energy according to Einstein's famous equation. The conversion is total, 100%. No chemical reaction comes close. Burning gasoline converts roughly 1/1000th of the fuel's mass into energy. A nuclear fission reaction converts about 1/10th of 1%. A fusion reaction does better, converting around 0.7%. Antimatter beats them all by orders of magnitude. For interstellar travel, the implications are staggering. A spacecraft running on antimatter would need almost no fuel by comparison to any other engine. To reach Proxima Centauri at 10% of light speed, a fully fueled antimatter rocket would only need a few tons of antimatter for the entire mission. No mountain of hydrogen, no fleet of fusion pellets. A tiny tank of frozen, magnetically suspended antiprotons would do the job. The catch is how much antimatter exists. Antimatter does occur naturally. Cosmic ray collisions in the upper atmosphere produce a few antiparticles every second. Some particles inside Earth's radiation belts are antiprotons, trapped briefly before annihilating. None of these natural sources can be collected in useful amounts. Manufactured antimatter is a different story. Particle accelerators, like the Large Hadron Collider in Switzerland or the Fermilab Tevatron in Illinois, can produce antiprotons on demand. The technique involves slamming high-energy particles into metal targets and capturing the antimatter that scatters off in the debris. The total amount ever made by humans, summed across every laboratory in history, is a few nanograms. A nanogram is 1/1000th of a gram. A grain of salt weighs about 60 milligrams, or 60 million nanograms. Every antimatter atom ever produced by humanity, gathered together, would not be visible without a microscope. The cost is also astronomical. A single gram of antiprotons would cost, by current estimates, somewhere around $100 trillion to manufacture. That number is rough. Estimates vary widely. Even the most optimistic projections put a gram in the tens of billions of dollars range. For interstellar travel, the spacecraft needs not a gram, but tons. Storage is the next obstacle, Antimatter cannot touch any normal matter without immediately annihilating. The spacecraft would need a containment vessel that holds the antimatter completely suspended in vacuum using powerful magnetic fields for the entire mission. A containment failure would mean instant catastrophic detonation. A small leak, on the scale of a milligram, would vaporize the spacecraft. Several research groups continue to study antimatter storage. Penning traps, magnetic bottles, and electromagnetic levitation cages have all held tiny amounts of antimatter for short periods. The current record stands at a few minutes for thousands of antiprotons. The mission needs decades of storage for trillions of antiprotons. The gap is vast. NASA has occasionally funded antimatter propulsion studies. The most famous, called the Antimatter-Initiated Microfusion Engine, would use tiny amounts of antimatter to ignite fusion reactions in pellets, getting the energy boost without. Needing massive antimatter quantities. The hybrid approach is promising. The barriers are still formidable. While engineers wrestled with how to carry fuel that does not yet exist in usable amounts, another idea proposed not carrying fuel at all. The fuel would simply be scooped up, free, from space itself. In 1960, an American physicist named Robert Bussard published a short paper that captured the imagination of every science fiction writer for the next 30 years. The idea was elegant. Space contains hydrogen. A spacecraft moving fast sweeps through that hydrogen at high speed. Build a giant funnel at the front of the ship. Use a magnetic field to scoop hydrogen into a fusion reactor at the rear. The reactor fuses the hydrogen and uses the released energy to push the ship forward. Faster ship, more hydrogen scooped per second, more thrust. The system feeds itself. A spacecraft using this design would never run out of fuel. The whole galaxy becomes a giant fuel station. The faster you go, the better your engine works. Bussard's paper showed that such a ramjet could, in theory, accelerate continuously. Given enough time, the spacecraft could approach the speed of light. Time dilation effects would let crews cross enormous distances in subjective decades, even if Earth experienced thousands of years passing. The concept inspired Carl Sagan, who described it favourably in his 1970s book Cosmos. Larry Niven and Paul Anderson wrote novels featuring ramjets. Engineers spent decades trying to make the math work. Then the math fought back. The first problem was the fuel itself. Interstellar hydrogen is mostly in atomic form, single atoms drifting through the vacuum. Fusing single hydrogen atoms is one of the hardest reactions in physics. Stars do it, but they need cores compressed for billions of years to make it happen. A spacecraft engine cannot replicate stellar conditions. The reaction is too slow, too inefficient to power a moving vessel. Fusion reactors on Earth use deuterium and tritium, heavier hydrogen variants. Both are rare in the interstellar medium. The hydrogen out there is the wrong kind for any practical reactor we know how to build. The second problem was drag. The same magnetic field that scoops hydrogen into the reactor also slows the spacecraft. Every hydrogen atom captured by the field transfers a tiny bit of momentum from the ship to the field. As the ship moves faster, the drag grows. At some velocity, the drag from scooping equals the thrust from fusion. Acceleration stops. Calculations done in the 1980s and 90s pinpointed the exact velocity where the math breaks. For a Bussard ramjet using ideal fusion of interstellar hydrogen, the maximum speed turned out to be only a small fraction of light speed. Some studies put the cap at around 12%, others lower. The endless acceleration promised by the original paper was an illusion. The third problem was the funnel itself. To scoop enough hydrogen to feed a fusion reactor, the magnetic intake field would need to span thousands of miles wide. Generating a magnetic field that big, that strong, requires massive amounts of power. The power has to come from somewhere. The fusion reactor was supposed to provide it, but the reactor was supposed to be powered by the scooped hydrogen, and the hydrogen scoop required power. The whole concept is locked in a loop. By the 1990s, the consensus among propulsion researchers was that the Bussard ramjet, in its original form, would never work. Modified versions, where the scoop only collects helium-3, or where the spacecraft carries some onboard fuel and uses scooping only as a supplement, remain on the drawing. Bored. The original dream of a starship that fuels itself forever has been quietly buried. Even if propulsion problems had a clean solution, another enemy waits for the crew. Time itself. A spacecraft moving at high speed does not experience time the same way as the people back home. This is one of Einstein's strangest predictions, and it has been confirmed countless times in laboratory experiments and with atomic clocks flown around the world on commercial. Airliners. As an object moves faster, its internal clock runs slower compared to a stationary observer. At normal speeds, the effect is microscopic. A pilot flying a passenger jet for 30 years arrives back on the ground a few hundred milliseconds younger than someone who stayed home. Real, measurable, but hardly noticeable. At interstellar speeds, the effect becomes dramatic. A spacecraft moving at 50% of the speed of light experiences time roughly 15% slower than Earth. At 90%, the slowdown is more than half. At 99%, the difference grows to a factor of 7. At 99.9%, it is over 20. For a crew, this looks like a gift at first. Imagine a mission to Proxima Centauri at 90% of the speed of light. The trip is roughly 4.7 light-years one way. From Earth's perspective, the journey takes about 5.2 years. From the crew's perspective, the journey takes only about 2.3 years. The crew ages slower than the people they left behind. A round trip would mean the crew ages about 4.6 years total. Earth, meanwhile, ages over 10 years. That gap may not sound terrifying. Push the speed higher and the gap explodes. A mission to a galaxy 4 million light-years away at 99.9% of the speed of light would take the crew only about 170,000 years subjective time. From Earth's perspective, the trip would take more than 4 million years. The crew, if they could survive that long inside the ship, would return to find every civilization they ever knew long extinct. Even for a closer mission, the gap creates problems. Communication becomes a tragedy. A crew on a starship at high relativistic speed sends messages home, but those messages take years, sometimes decades, to arrive. By the time Earth replies, the crew is much older, but Earth is even older still. Conversations across decades are impossible. Each message arrives in an utterly different world than the one that sent the previous reply. Family ties dissolve. A crew member with a young child on Earth might return to find that child is now an old man, or already dead. Spouses age and die while the traveller barely changes. Mission planners take this into account. Volunteers for hypothetical interstellar missions tend to be people without close family ties. Older astronauts. People at the end of their careers who have already said goodbye to their previous lives. There is a darker version of the problem. Time dilation only kicks in significantly at relativistic speeds, above roughly 10% of light speed. Most realistic mission designs do not reach those velocities. A trip to Proxima at 5% of light speed produces almost no time dilation. The crew ages exactly as fast as Earth, 80 years out, 80 years back. For the crew of such a mission, the slow trip is a one-way trip. The Earth they left will be utterly transformed by the time they return, if they return at all. Every friend, every family member, every culture they remember will be gone. That gap kills not the body, but the connection. And the connection itself is delicate, tied to a signal that fades fast. A radio signal from Proxima Centauri B takes 4.24 years to reach Earth. This is not an engineering problem. This is the speed of light. Nothing in the universe moves faster. No technology, no clever trick, no future invention can shorten that delay. As Einstein's special relativity established, and every experiment for over a century has confirmed, Light speed is the absolute ceiling for information transmission. The result is a communication architecture unlike anything humans have ever managed. Picture a probe arriving at Proxima B. The probe takes pictures of the planet's surface. It analyzes the atmosphere. It checks for water, for temperature, for any sign of life. The probe compresses the data and beams it home. The signal travels at light speed across the vacuum. For 4 years and 3 months, the signal moves through interstellar space, getting weaker, spreading out. By the time it reaches Earth, the signal is incredibly faint. A receiver would need to be enormous to catch it. Earth receives the data. Scientists cheer. Then they realize what they are looking at. The pictures are 4 years old. The atmosphere readings are 4 years old. Anything that has changed at Proxima B in the last 4 years, the probe has not yet seen. The probe might already be destroyed by a flare from the star, and Earth would not know for years. Now Earth wants to send a command, maybe to redirect the probe, maybe to focus the cameras on a specific feature. The command travels back across the same gap, 4.24 years out. Then the probe has to receive, process, act, and transmit again. Another 4.24 years for the result to come back home. A single round-trip conversation, nearly 9 years. For a crewed mission, the implications are heavy. A spacecraft halfway to Proxima needs help with a malfunction. The crew sends a distress message. Earth's flight controllers receive it 2 years later. Engineers spend a few weeks working out a solution. The fix gets transmitted back. By the time the crew receives the answer, more than 4 years have passed since the original problem. Real-time guidance is impossible. The crew has to be self-sufficient. Every emergency procedure, every medical protocol, every system repair manual, every spare part the mission might need, must be on board from the start. The signal strength problem is also brutal. A radio transmitter on a small spacecraft cannot generate enough power to send a strong signal across light years. The Pioneer probes, launched in the early 1970s, became too faint to hear after a few decades, even though they were closer than any star. Voyager transmits at about 23 watts of power. By the time the signal arrives at Earth, the receiver picks up about 1/1000th of 1/1000th of 1 watt. Receiving anything at all requires giant dish antennas, like the 70-meter dishes of NASA's Deep Space Network. For a probe at Proxima Centauri, the received signal would be even weaker. Receiving useful data would require building a much larger dish on Earth, possibly an array of dishes spread across continents, all pointed at the same patch of sky. The Square Kilometre Array, currently being built across South Africa and Australia, will be the largest radio telescope in history. Even that array would struggle to pick up a weak signal from a Proxima probe. The harder option is to send a signal big enough to receive easily, which means a heavy transmitter on board. Heavy transmitters mean more launch mass. The mass problem returns again, dressed up in a different uniform. The whole architecture trembles on the edge of what humans know how to do. If a crew cannot reach Proxima in a single lifetime, then the answer might be to send several lifetimes at once. The concept is called a generation ship. The basic idea has been kicked around since the 1920s, when Russian rocket pioneer Konstantin Tsiolkovsky first sketched it out. Send a spacecraft so large that it functions as a self-contained world. The original crew lives, has children, raises those children, and dies on board. The grandchildren grow up never having seen Earth. The great-grandchildren arrive at the destination. The engineering numbers force the design to be huge. A realistic generation ship needs internal living space measured in cubic miles. The hull would have to enclose farms, water reservoirs, manufacturing shops, schools, hospitals, recreation areas, and burial chambers. Every system that supports civilization on Earth has to be replicated inside the spacecraft. Without resupply. Without rescue. Most modern designs propose a rotating cylinder, miles long and thousands of feet across. The rotation creates artificial gravity through centrifugal force. People walk on the inside of the cylinder's hull, pressed outward by the spin, while the central axis stays in zero gravity for low-stress activities and storage. The hull itself becomes a problem. Cosmic rays bombard the spacecraft constantly. Shielding the entire interior would require thick walls of water, hydrogen-rich plastic, or asteroid rock. A typical estimate calls for at least a few feet of dense material around the entire habitable zone. That much shielding adds enormous mass, which makes acceleration harder, which forces a longer journey, which means more shielding. The propulsion system has to operate for centuries. A generation ship moving at 1% of light speed reaches Proxima in about 400 years. That assumes the engines work the entire time, that the crew never has to slow down for repairs, and that nothing in interstellar space damages the spacecraft beyond repair. Building a fusion engine that runs for 400 years without breakdown is not currently possible. Modern jet engines, which are far simpler than fusion drives, get rebuilt every few thousand hours of operation. A generation ship's engine would need to log millions of hours of continuous operation with no factory available. The crew has to maintain everything themselves. This includes the ability to manufacture new parts when old ones fail. The ship needs a complete industrial base. Foundries to melt metal, machine shops to cut new components, electronics labs to build replacement circuit boards, chemists to synthesize medicines and lubricants, geneticists to maintain the food crops. Every skill that civilization on Earth requires must be present on the ship, and it must be passed down across generations with no opportunity to import expertise. The training problem is enormous. A child born on a generation ship grows up in a world made entirely by their parents and grandparents. They never see open sky. They never feel rain. They never meet a stranger. Their entire universe is the ship, and everything they know about Earth comes from records and stories. By the third or fourth generation, Earth is a legend, not a memory. Some thinkers have argued the crew might lose interest in completing the mission. The grandchildren did not sign up for the journey. They were born into it. Their life inside the ship is the only life they know. The destination, 4 light years away, is just an abstract idea. A generation ship needs more than engineering. It needs a culture stable enough to hold the mission together for centuries. That stability has been tested on a much smaller scale right here on Earth, and the results were not encouraging. In 1991, in the high desert of Arizona, 8 people walked into a sealed glass building covering 3 acres and locked the doors behind them. The building was called Biosphere 2. The first biosphere in this naming scheme was Earth. The second was an experiment to see whether humans could create a smaller version that worked the same way, completely closed off from the outside world. The structure cost about $150 million to build. It contained a miniature rainforest, a tiny ocean with a coral reef, a savanna, a marshland, a fog desert, and a farm area where the residents would grow their own food. Roughly 3,800 species of plants and animals were inside. The mission was simple in concept. Live inside for 2 years, eat only what you grow, breathe only the air the plants make, drink only the water the system recycles. If it worked, the experiment would be a proof of concept for closed life support systems on space stations, lunar bases, and ultimately, generation ships heading to other stars. The mission failed in almost every measurable way. The first crisis was air. The oxygen level inside Biosphere 2 started dropping within a few months. By 18 months in, the oxygen had fallen from 21%, the normal Earth level, to roughly 14%. That is the equivalent of standing on top of a 14,000-foot mountain. The crew started suffering from hypoxia. They lost weight. They struggled to think clearly. Several of them showed signs of mild brain damage from the chronic low oxygen. The cause turned out to be the concrete in the structure itself. The fresh concrete was absorbing oxygen as it cured, locking the gas into the walls. The plants could not produce enough new oxygen to keep up. Mission Control had to break the seal and pump in fresh oxygen, twice. The closed system was not closed. Food production also collapsed. The crew had calculated their farm could feed 8 people. The actual yields fell short. Crops failed. Pollinators died off. The crew lost an average of about 16% of their body weight in the first year. They were chronically hungry. The wildlife inside Biosphere 2 suffered worse. Most of the vertebrate species died. Most of the insects died. Cockroaches and ants thrived, in plagues, outcompeting the species that were supposed to maintain the food web. Morning glory vines exploded across the rainforest section, smothering native plants. The crew also fractured socially. 8 intelligent, motivated, carefully selected people, locked together for 2 years with limited food and oxygen, broke into 2 factions. The split lasted long after they emerged from the dome. Members from opposite groups still refused to speak to each other decades later. A second mission, in 1994, ended early when the crew sabotaged the experiment by opening the airlock from the inside. The project was shut down shortly after. Biosphere 2 failed in a controlled environment, on Earth, with mission planners on the outside able to send help, modify equipment, and ultimately rescue the participants. A generation ship gets none of those advantages. The ship is sealed for centuries. Mission control is years away by radio. There is no rescue. There is no oxygen tank to pump in. If a closed ecosystem could not survive 2 years on Earth, the prospect of running one for 4 centuries between stars demands solutions that science has not yet found. The biological problem stretches further than air and food. The crew itself faces a slow genetic crisis. A generation ship is a tiny breeding population. For most of human history, our species has lived in groups of hundreds to thousands. Genetic diversity has been preserved by intermixing with other groups, by trade routes, by migration. A generation ship cuts off all of that. The crew is whatever the original mission planners selected. Their descendants will have only those genes to draw from for centuries. Inbreeding becomes the central biological threat. Geneticists who study small populations have long known the danger. When a breeding group is too small, harmful recessive genes start showing up in offspring at much higher rates. Birth defects increase. Fertility drops. Children get sicker. Over generations, the population can collapse entirely. Researchers have studied this in island species, in zoo breeding programs, and in isolated human communities. The cheetah, for example, went through a genetic bottleneck thousands of years ago that left every cheetah today with nearly identical genes. The species is so genetically uniform that one disease could wipe them all out. For a generation ship, the question becomes mathematical. How many people are needed to keep the population genetically healthy across hundreds of years? The answer has shifted as the science improved. Early estimates from the 1970s suggested that a few hundred people might be enough. Later research pushed the number higher. A 1997 paper proposed a minimum of around 500 crew members. By the 2010s, anthropologist John Moore at the University of Florida ran detailed simulations and concluded that at least 160 individuals would be needed. For an 8-generation mission, assuming careful breeding management. Other researchers argued the number should be much larger. A 2018 study by Frederick Marin and Camille Belufi suggested that for a 5,000-year mission, the minimum healthy crew size would be roughly 98 individuals if breeding was strictly managed. Without management, the number jumped to several hundred. The key word in those studies is management. The crew cannot simply pair off based on personal preference. They have to follow breeding rules designed to maximize genetic diversity in each generation. Children might be assigned to specific parents based on genetic compatibility. Personal romance becomes a luxury the species cannot afford. That kind of social control creates new problems. People rebel against arranged reproduction. Cultures built on it have always been unstable. A crew that fights the breeding program risks the genetic future of the entire mission. The numbers ramp up further if you require buffer for accidents. Some crew members will die before reproducing. Others will be infertile. Some will have children who cannot themselves reproduce. The population needs reserve capacity to absorb those losses without collapsing the gene pool. A realistic generation ship probably needs at least 500 people, possibly several thousand, to keep going for 400 years. Each crew member adds mass. Each crew member needs food, water, oxygen, living space, medical care, education, and shelter. The mass cost of a 1,000-person crew is enormous compared to the cost of a small probe. The genetic bank itself can be supplemented with frozen sperm and egg samples, plus banked embryos, to expand the available genetic diversity beyond the living crew. Some mission concepts rely heavily on these banks, treating the living crew as caretakers and reproducing primarily through stored material. That solution shifts the problem to long-term storage. Frozen biological material does not last forever. Even at extremely low temperatures, slow degradation occurs. Maintaining a viable embryo bank for 400 years is an experiment that has never been run. While the genetics threaten the crew slowly, another enemy hits them constantly, from every direction, every second of the journey. Earth shields its inhabitants in ways most people never appreciate. Two layers protect us. The first is the magnetic field generated by Earth's molten iron core. That field deflects most of the charged particles streaming through space toward our planet. The second is the atmosphere itself, which absorbs nearly all of the radiation that gets past the magnetic field. Together, they form a shield so effective that ground-level cosmic radiation dose is roughly 50 times lower than the dose received in deep space. A spacecraft heading to Proxima Centauri leaves both shields behind on day one. What remains is a steady rain of particles that have been travelling through interstellar space for millions of years. These particles fall into two main categories. The first category is solar energetic particles. The bright star at the centre of our system, like all stars, occasionally emits massive bursts of charged matter during solar flares. A spacecraft inside our solar system has to deal with these regularly. Once the spacecraft leaves the heliopause, the protective bubble of solar wind that wraps around the entire planetary system, that source fades. The second category is galactic cosmic rays. These are particles, mostly stripped atomic nuclei, accelerated to enormous speeds by supernova explosions and other violent events across the galaxy. They come from every direction at once. They travel at nearly the speed of light. A typical galactic cosmic ray hits with energy that no shielding material can fully stop. When a high-energy particle slams into a spacecraft hull, the impact creates a shower of secondary particles. Each of those secondaries can, in turn, create more particles. The cascade spreads through the ship like a tiny indoor lightning storm. Some of those secondaries pass through human tissue. Each passage damages cells. The damage accumulates. Astronauts on the International Space Station, only 250 miles above Earth, already receive about 100 times the radiation dose of someone on the ground. They are still inside Earth's magnetic field, just above it. The dose is high enough that NASA limits how long any single astronaut can stay aboard the station. A crew on a years-long voyage to Mars would receive an even higher dose. Estimates suggest a round trip to Mars could deliver a lifetime's worth of allowable radiation in a single mission. The cancer risk for the returning crew jumps significantly. A crew on a multi-decade voyage to Proxima receives doses that no current radiation safety standard would permit. Shielding helps, up to a point. A few inches of aluminum, the typical hull material for spacecraft, blocks some radiation but produces secondary particle showers when high-energy galactic rays hit. The secondaries can actually be more dangerous to soft tissue than the original particle. Thick shields of water or hydrogen-rich plastics work better. The problem is mass. A water shield thick enough to block most galactic cosmic rays would weigh more than the entire spacecraft. Some designs propose surrounding the crew quarters with the spacecraft's water supply, using the drinking and bathing water as shielding. The water has to be there anyway, so the mass cost is partially absorbed. Other designs propose magnetic shielding, using powerful onboard magnets to deflect charged particles before they hit the hull. This idea works in principle. In practice, generating a magnetic field strong enough to be effective requires enormous power, and superconducting magnets that can run for decades without failure do not yet exist. The slow accumulation of damage attacks every organ. The brain may suffer the most. The human nervous system is delicate. A neuron is a long, thin cell with branching tendrils that pass electrical signals to its neighbours. Each neuron in your brain has thousands of connections. The whole system depends on those connections staying intact, working in coordinated patterns for your entire life. Brain cells, unlike most cells in the body, mostly do not regenerate. The neurons you have now are largely the same ones you were born with, plus a small number generated in a few specific regions throughout life. When neurons are damaged, the brain rewires around them if possible. If too many are damaged, function declines. A high-energy galactic cosmic ray passing through brain tissue can shred multiple neurons in a single track. The track is microscopic, but the damage is permanent. NASA has been studying the effects of cosmic radiation on brain tissue for years. Researchers at the University of California, Irvine ran a series of experiments in the 2010s exposing mice to particle beams that mimicked the radiation environment of deep space. The mice that received doses equivalent to a Mars round trip showed measurable impairment. The mice could not learn new tasks as quickly. Their memory degraded. Their behaviour became erratic. Some showed signs of chronic anxiety and depression-like states. Brain tissue analysis revealed widespread damage to the dendrites, the branching structures that connect neurons to each other. The damage was permanent. The mice did not recover. The implications for a long interstellar mission are alarming. A crew on a generation ship would be exposed to cosmic radiation continuously for decades. Some crew members would receive doses far higher than anything tested on Earth. The cumulative effect on cognition, on memory, on emotional stability, on basic motor function is unknown. Animal studies suggest the effects would be severe. A crew that loses cognitive function during a critical mission phase could fail catastrophically. Imagine the lead engineer making mistakes during a fusion engine repair because radiation has eroded their problem-solving ability. Imagine the pilot misreading instruments during an emergency. Imagine the doctor unable to remember dosage calculations. The brain is also where decision-making lives. A crew with impaired judgment might make catastrophic choices about resource use, breeding programs, or social conflicts. The whole mission depends on the crew thinking clearly for centuries. Radiation damage threatens that foundation directly. There are partial defenses. Pharmaceutical research is exploring drugs that might protect brain tissue from radiation damage. Some compounds, called radioprotectors, can limit the chemical fallout from particle impacts. Others might encourage cellular repair after damage occurs. None has yet been proven effective for the kind of chronic exposure a long-duration crew would face. Genetic engineering offers another possibility. In theory, future crew members could be modified to have more efficient cellular repair mechanisms or stronger natural antioxidant production. This idea sits at the edge of current science. The ethical implications are enormous. The technology to safely make such modifications in adult humans does not yet exist. The brain is also vulnerable to a separate problem related to deep space environments. Without a normal day-night cycle, without seasons, without the social rhythms of life on a planet, the human nervous system drifts. Sleep cycles fail. Hormone levels go off. Mood disorders spike. Crews on the International Space Station already report significant psychological strain after just 6 months. A generation ship crew faces decades, then centuries of those effects, with no relief. If the brain might be saved by sleeping through the journey, that question takes us into another realm entirely. Science fiction has loved one solution to long voyages for decades: freeze the crew. Wake them up at the destination. No aging, no boredom, no decades of life support consumption. The reality of cryogenic preservation is messier. Cooling a human body below freezing causes ice crystals to form in cells. Each crystal acts like a tiny knife, slicing membranes apart from the inside. Even a brief exposure to sub-zero temperatures kills most tissues. Without protection, a frozen human is a ruined human. Cryobiologists have spent decades trying to solve this problem, but breakthroughs have come slowly, in pieces. The first major step was the development of cryoprotectants, chemicals that prevent ice from forming inside cells. Glycerol, dimethyl sulfoxide, and various sugars work to varying degrees. When tissues are saturated with the right cryoprotectant before cooling, the cellular fluid turns into a glass-like solid rather than crystalline ice. The cells survive the temperature drop intact. This process, called vitrification, has been used successfully on small samples. Sperm cells, eggs, and embryos are routinely vitrified for fertility treatments. Some organs, like rabbit kidneys and small samples of human heart tissue, have been successfully vitrified and rewarmed in laboratory experiments. The whole human body is a different scale of problem. A complete person contains roughly 30 trillion cells, organized into hundreds of distinct tissue types, all of which need different cryoprotectant concentrations and cooling. Rates to survive. Saturating the entire body uniformly is extraordinarily difficult. The blood vessels distribute the cryoprotectant inward, but the rate of penetration varies between organs. Some tissues take in the protective chemicals quickly. Others absorb them slowly, leaving regions of unprotected ice formation. Rewarming is just as fragile. The body has to thaw evenly, at exactly the right rate, without forming ice during the warm-up phase. Too fast, and parts of the body cook while others remain frozen. Too slow, and ice crystals form during the temperature transition. No human has ever been successfully vitrified and revived. The closest experiments involve cryopreservation of hopeful clients at companies like Alcor in Arizona, where bodies are frozen after legal death in the hope of future technology. Being able to revive them. The viability of that revival has never been demonstrated. NASA has investigated a different approach for long missions. The agency funded a study called Aerospace Corporation's Torpor program, which looked at inducing a state similar to hibernation in human crews. Bears and other mammals lower their metabolism dramatically during winter, slowing aging and reducing food and oxygen needs. The Torpor study asked whether humans could be induced into a similar state for weeks or months at a time. The mechanism would be a combination of mild cooling, sedation, and intravenous nutrition. The body temperature drops a few degrees, metabolism slows, oxygen consumption drops. The crew sleeps for weeks, then wakes briefly to perform critical tasks before going back under. Initial results showed the technique might be feasible for trips lasting weeks or months. Some hospital patients have been induced into therapeutic hypothermia for short periods after cardiac arrest. The body tolerates short-term cooling reasonably well. For interstellar missions, the technique would need to work for years or decades. That extended use has never been tested. The long-term effects on muscle wasting, organ function, and cognitive recovery are unknown. Research continues at modest funding levels. Several aerospace companies and university labs are working on the problem. The leading concepts remain on paper. No working prototype has demonstrated multi-year human stasis. Even if the body survives the long voyage, another fragile system is harder to keep intact than tissue: the mind itself. In 1999, a Russian crew of 8 men and 1 woman locked themselves into an isolation chamber outside Moscow for 440 days. The experiment, called Sphinx 989, was meant to simulate the psychological stress of a long-duration Mars mission. The crew had volunteered. They were screened, trained, and motivated. They had radio contact with mission control. They had video calls with family. They had work to do, exercise routines, recreational activities. The experiment ended in violence. About 4 months in, 2 crew members got into a fistfight. The fight was so severe that one man's blood spattered across the chamber walls. Around the same time, the male commander of the mission attempted to kiss the only female crew member without consent. Twice. She locked herself in her cabin. Mission Control had to intervene. After that, the crew installed locks on the doors between the Russian and international sections of the chamber. The crew split into factions. Trust collapsed. The remaining months were spent in barely controlled hostility. This was a 400-day experiment. On Earth. With the option to leave at any time. A generation ship would face the same pressures, multiplied 100-fold, with no exit. Psychological research on isolation has produced consistent findings across many studies. Submarine crews, Antarctic expedition teams, prison inmates in solitary confinement, and astronauts on long-duration space missions all show predictable patterns of mental degradation when cut off from normal society. The first phase is excitement, followed by adjustment. Most people adapt to a confined environment within the first few weeks. The second phase, after roughly 6 to 12 weeks, is depression and irritability. Conflicts between crew members start to emerge, sleep patterns deteriorate, people become emotionally numb. Some develop physical symptoms with no clear medical cause. The third phase, sometime between 3 and 6 months, is interpersonal breakdown. Small irritations become major grievances. Old grudges resurface. Crew members start seeing enemies where none exist. The Russian word for this state is asthenia, a kind of mental exhaustion that affects every aspect of life. The fourth phase, if the mission continues long enough, is described by researchers as final stage burnout. The crew loses motivation, loses interest in mission objectives, and starts going through the motions. Productivity collapses. Creativity vanishes. Even basic tasks become difficult to complete. For a multi-decade mission, the crew enters this final phase and stays there for the rest of the voyage. There are partial defences. Careful crew selection helps. Psychological compatibility testing, group therapy training, and personality screening can reduce the likelihood of catastrophic conflicts. Regular communication with home, even with multi-year delays, gives the crew an emotional anchor. Variety in the daily routine helps. Mission planners design schedules with rotating tasks, recreational activities, and social events. Spacecraft layouts try to provide private spaces alongside common areas, so crew members can have moments of solitude when needed. None of these strategies fully solves the problem. The fundamental fact is that humans evolved in tribal groups of 50 to 150 people, surrounded by nature, with constant change and opportunity. A generation ship offers the opposite. Tiny social pool. Fixed environment. Endless monotony. The first crew might hold together. The second generation, born into the ship, may have a different psychology entirely. They never experienced anything else. Their normal is the ship. Whether that helps them cope or makes them weirder in ways we cannot predict is an open question. The destination itself has its own threats. The star at the heart of Alpha Centauri's lonely red companion turns out to be a violent neighbour. Red dwarf stars are murder. This sentence sounds dramatic, and it is also, by current astronomical research, broadly accurate. Red dwarfs make up about 3/4 of all stars in the Milky Way. They are smaller, cooler, and dimmer than our home star. They burn slowly, lasting hundreds of billions of years, far longer than the universe is currently old. They are also the most violent ordinary stars in the galaxy. Proxima Centauri is a textbook example. The star has a mass of about 12% of our home star's mass, and a radius of about 14%. It is so dim that despite being our nearest stellar neighbour, no human eye can see it without a telescope. The star sits more than 150 times below the visibility threshold for the naked eye. Yet Proxima flares often, violently, with no warning. In March 2016, astronomers detected a flare from Proxima that increased the star's brightness by a factor of 68 in seconds. In May 2019, an even bigger flare hit. The star brightened by a factor of 14,000 in the ultraviolet wavelengths. The flare lasted only 7 seconds. The energy released equaled millions of years of normal stellar output, all dumped into a brief explosion. Proxima Centauri B, the planet that sits in this star's habitable zone, is bathed in those flares constantly. The habitable zone of a red dwarf is much closer to the star than the equivalent zone around our home star. The reason is simple. The star is dimmer, so to receive enough energy for liquid water, the planet has to be much closer. Proxima B orbits at about 5% of the distance from Earth to our home star. The planet completes a full orbit in 11 days. Every flare Proxima emits hits the planet hard. Each major flare delivers an X-ray and ultraviolet pulse, hundreds or thousands of times stronger than anything our home star ever sends to Earth. Without a strong magnetic field and a thick atmosphere, the planet's surface would be sterilized repeatedly. The radiation would shred any complex molecules. Water, even if present, would be split apart into hydrogen and oxygen by the constant ultraviolet bombardment. The hydrogen would escape into space, leaving the planet drier each cycle. Astronomers have been studying whether Proxima B's atmosphere has survived this onslaught. The current state of evidence is uncertain. Some models suggest the atmosphere has been completely stripped, leaving Proxima B as an airless rock. Other models suggest a thick atmosphere has hung on, possibly thanks to a strong magnetic field protecting the planet. We do not know which model is right. We will not know until a probe arrives. For a crew thinking about going there, the implications are heavy. Even if Proxima B has a survivable atmosphere, surface conditions during a major flare would be lethal. A human standing on the surface during a Class M flare would receive radiation doses comparable to a nuclear blast. The flares come without warning, sometimes multiple times per month. Survivable habitation would require permanent underground shelter, with crews sprinting indoors any time the sky lit up unexpectedly. The star is also highly active in the magnetic spectrum. Its magnetic field is much stronger than the equivalent field around our home star. The field generates a steady stream of energetic particles, hitting the planet with what amounts to a constant solar wind. A spacecraft in orbit around Proxima B would face the same constant assault. The destination is hostile in ways the brochure never mentioned. The day-night cycle at Proxima B adds another twist that makes the surface even worse. Imagine a planet with no day, or no night. Forever. This is the reality of tidal locking, and it applies to most planets orbiting close to red dwarf stars. Proxima Centauri B is almost certainly tidally locked. The planet's rotation period equals its orbital period. One side faces the star permanently, the other side faces deep space permanently. The mechanism is simple gravitational physics. When a planet orbits very close to its star, the star's gravity pulls more strongly on the planet's near side than its far side. That difference in gravitational force creates a tidal bulge. Over millions of years, the friction inside the planet from this bulge slows the planet's rotation, until eventually the same face always points toward the star. Earth's moon is tidally locked to Earth. The same face of the moon has pointed at us since prehistoric times. The far side, which we never see from Earth's surface, is just as real, but forever hidden. Proxima B is locked to its star in the same way. The implications for habitability are dramatic. The day side, the half of the planet always facing Proxima Centauri, receives constant heat. Surface temperatures could reach hundreds of degrees Fahrenheit, depending on the atmosphere. With a thick atmosphere, heat could circulate around the planet, moderating the extremes. Without an atmosphere, the day side becomes a baked desert, with no shade and no relief. The night side, the half of the planet always facing away, receives no direct light or heat from the star. Surface temperatures could drop to hundreds of degrees below zero. Atmospheric gases might freeze solid and fall as snow. Anything liquid on the night side would solidify and stay frozen. Between these two extremes lies the terminator, a narrow ring around the planet where the star sits permanently on the horizon. The terminator is the only zone where temperatures might be tolerable. Above the dayside horizon, conditions get hotter until they become unsurvivable. Below the nightside horizon, conditions get colder until they become unsurvivable. The terminator zone might be a few hundred miles wide. It is the only place on Proxima B where a human could potentially stand outside and not die. That zone is also a place of permanent twilight. The star never rises and never sets. It hangs at the same angle in the sky year after year, casting long shadows in one fixed direction. Nothing changes. There is no morning, no evening, no noon. The local weather inside the terminator zone is brutal. The temperature gradient between the hot day side and the cold night side drives massive winds across the boundary. Air heated by the day side rises and flows toward the night side at high altitude, cools, and returns at low altitude. The result is a constant gale of cold air blowing from the night side into the terminator zone, while warm air rushes in from the day side. Storms in the terminator might be permanent. Winds could reach hundreds of miles per hour. Dust and ice particles flung at those speeds would scour any surface or structure exposed to them. A human settlement on Proxima B would have to be built underground or inside reinforced shelters in the terminator zone. The colonists would never see a sunrise. They would never feel a normal day. Their entire life would be lived in a fixed twilight, with the wind howling outside. That assumes the planet has an atmosphere at all. Whether it does is still a guess. The single most important thing astronomers do not know about Proxima B is whether the planet has air. A planet's atmosphere is the difference between a habitable world and a sterile rock. Earth has air, and Earth is alive. Mars has thin air, and Mars is mostly dead, though possibly hosting microbes underground. The Moon has essentially no air, and the Moon is a barren wasteland with no life of any kind. Proxima B might have any of these conditions. Current measurements cannot distinguish between them. The reason is technical. Detecting an atmosphere on an exoplanet requires watching the planet pass in front of its host star, then analysing the starlight that filters through the planet's air. Different gases absorb different wavelengths of light, leaving fingerprint patterns in the spectrum. By comparing the starlight before, during, and after the transit, astronomers can read off what gases are present. Proxima B does not transit its star from our viewing angle. The orbit is tilted relative to Earth's line of sight. The planet never crosses the face of Proxima Centauri from our perspective. This single geometric fact makes the standard atmosphere detection technique impossible. Astronomers have tried other methods. Some have looked for the planet directly using high-resolution imaging. Proxima B is too close to its host star and too dim to image with current telescopes. The James Webb Space Telescope, the most powerful infrared observatory ever built, can study the atmospheres of larger and farther exoplanets, but Proxima B sits in a difficult observational sweet spot. Future instruments might be able to do the job. The European Extremely Large Telescope, scheduled for first light in 2028, will have a primary mirror nearly 40 meters across. With advanced imaging techniques, the telescope might be able to capture light directly from Proxima B and analyze it. Even with that capability, distinguishing between a thick atmosphere and a thin one will be difficult. In the meantime, astronomers rely on models. The models start with what is known: Proxima B's mass, its distance from its star, the host star's flare history, the age of the system. From those inputs, simulations can predict how much atmosphere the planet might have retained over billions of years. The answers vary widely. Some models suggest Proxima B lost its original atmosphere within the first few 100 million years of the system's existence, stripped away by the young star's intense flares. The planet would now be a bare rock, similar to the Moon but warmer. Other models suggest the atmosphere survived in some form. A magnetic field generated by a molten core could have deflected the worst of the flare radiation. Volcanic outgassing could have replenished gases lost to space, the planet might have a thick atmosphere of carbon dioxide and nitrogen, comparable to Earth's atmosphere or even Venus's much heavier blanket. A few models suggest a strange middle ground. The atmosphere on the day side might have been driven away by the constant heat and radiation, while the night side retains a thin layer of frozen gases on the surface. As the day side bakes and the night side freezes, gas migrates between them in a constant cycle. This pattern would be unlike anything in our solar system. Without direct observation, we cannot know which model is right. For mission planning, the uncertainty is paralyzing. A crew arriving at Proxima B might find a planet they can land on, walk around with appropriate suits, and study from a surface base. Or they might find a vacuum-exposed rock that offers no advantages over an asteroid. The mission profile, the equipment list, the survival probability, all depend on which version of Proxima B is real. The destination might not even be the right destination. Two other stars sit in the same neighbourhood, complicating every plan. Proxima Centauri does not stand alone. The star is part of a triple system, gravitationally bound to two larger companions. Alpha Centauri A and Alpha Centauri B form a tight binary pair, orbiting each other every 80 years. Proxima orbits much farther out, about 13,000 astronomical units from the central pair, completing a single orbit roughly every 550,000 years. The whole system, sometimes just called Alpha Centauri or Rigil Centaurus, is the closest stellar group to ours. Anyone making the trip to Proxima passes through or near the larger pair on the way. Alpha Centauri A is similar to our home star. Slightly larger, slightly hotter, slightly more luminous. The star has been compared to a near twin of our own. Alpha Centauri B is smaller and cooler, comparable to a common orange dwarf. Together the two stars form one of the most studied binary systems in the sky. For decades, astronomers have searched for planets around Alpha Centauri A and B. The hunt has been frustrating. The two stars complicate each other's planetary systems. Their mutual gravity creates unstable orbits in many regions where planets might form. A stable planet has to either orbit one star very closely, ignoring the influence of the other, or orbit the entire pair from a great distance. In 2012, a team announced the discovery of a planet around Alpha Centauri B. The planet was reported to be Earth-sized and orbiting close to the star. The announcement made headlines worldwide. Within a few years, follow-up studies questioned the discovery. The signal that had been interpreted as a planet appeared to be an artifact of the star's own activity, not a real world. The detection was retracted. In 2021, a more careful study found a possible signal of a planet around Alpha Centauri A. The planet, if real, would be roughly Neptune-sized and would orbit in the star's habitable zone. The detection was tentative. Confirmation has not yet arrived. The question of whether Earth-like planets exist around Alpha Centauri A or B remains genuinely open. For a mission planner, the binary system creates a choice. Send the spacecraft to Proxima, where a confirmed rocky planet exists in a hostile environment. Or send the spacecraft to Alpha Centauri A or B, where a more pleasant climate might be available, but where the planets themselves are uncertain. The two stars also threaten any mission with their own gravity. A spacecraft heading for the system has to plan its trajectory carefully. Approaching too close to either star without adjustment risks being swung off course. The combined gravitational tugs of three stars at close range create a chaotic environment that simple Newtonian mechanics cannot easily predict. Some mission concepts propose using the gravity of Alpha Centauri A and B as a brake. A spacecraft approaching at high speed could, in theory, slingshot around one of the larger stars and shed velocity through the encounter. The geometry of such a maneuver would be intricate. A small targeting error at light-year distances could turn the slingshot into a fatal flyby. The light from the two larger stars also creates an issue. Proxima Centauri sits more than 10,000 astronomical units from its companions. From Proxima, the larger stars appear as bright points of light, much brighter than Venus appears from Earth. Any astronomer working at a Proxima base would look up and see two extremely bright stars in the sky, not far apart. Those companions could affect Proxima B's climate over very long timescales. Gravitational interactions between the three stars cause Proxima's orbit to wobble. Over many millennia, the planet's exposure to the wider environment shifts. The journey itself passes through a region of space we have never measured up close. Our home star sits inside a small bubble. The bubble is called the local bubble, a region of space about 1,000 light-years across where the gas density is unusually low. The bubble formed from a series of supernova explosions that swept material outward several million years ago. Our entire solar system has been drifting through this thin region for the last few 100,000 years. Beyond the local bubble lies thicker interstellar space. The transition is gradual. The gas density rises slowly as the spacecraft moves outward. For a probe heading to Proxima Centauri, the journey passes through a smaller cloud nested inside the local bubble. This region is called the local interstellar cloud, sometimes nicknamed the local fluff. The cloud is about 30 light-years across. Our solar system has been moving through it for the last 60,000 years and may exit within the next few thousand years. Beyond the local fluff sits a denser cloud called the G-cloud, currently surrounding Alpha Centauri. The boundary between the local fluff and the G-cloud is somewhere between us and our nearest stellar neighbour, but the exact location is unclear. This matters for any mission heading toward Proxima. Denser gas means more particles to slow the spacecraft, more dust to threaten the hull, and more material to interfere with magnetic shielding. A crewed mission would face a different radiation environment in the G-cloud than in the local fluff. The shielding requirements might shift partway through the journey. Astronomers have been trying to map the boundary using indirect methods. The interstellar medium absorbs starlight at specific wavelengths. By looking at the absorption patterns in the light from various nearby stars, researchers can build a rough map of where the dense regions sit. The map is rough. Voyager 1 and Voyager 2 have provided some ground truth. Both probes crossed the heliopause, the boundary where our home star's solar wind ends, and entered interstellar space. Voyager 1 crossed in 2012. Voyager 2 crossed in 2018. Both probes have been transmitting measurements of the interstellar medium ever since. The data has been surprising. The density of charged particles, the strength of the magnetic field, and the composition of the gas are not what models predicted. The interstellar medium is more complex than expected. Our understanding of what lies in the path between our solar system and Proxima is still being assembled. A crewed mission heading to Proxima would likely send precursor probes years in advance. Smaller, faster spacecraft would map the route, measuring density, dust concentrations, and magnetic field variations at various points along the trajectory. The crewed ship would adjust its course based on what the precursors found. This sounds straightforward. The problem is timing. A precursor probe sent 10 years before the crewed mission would arrive at Proxima decades before the crew. The data it sends back would reach Earth years before the crew launches. By the time the crewed ship is underway, the precursor data is already old. The data the crew really needs is data from the path the ship is currently flying. That data does not exist until the ship gets there. Unknown obstacles in the route may already be too late to dodge by the time they are detected. A small course error becomes a much bigger problem at interstellar distances, growing wider with every mile flown. Aiming a spacecraft is hard. Aiming a spacecraft over 4 light-years is brutal. Imagine standing in San Francisco and trying to throw a dart at a specific window on a specific apartment building in Tokyo. The two cities are about 5,000 miles apart. A throw that is 1 degree off the perfect angle would miss the window by tens of miles, far enough to land somewhere on the open ocean, never reaching the target city at all. Now multiply the throw distance by 5 trillion. That is the scale of pointing a probe at Proxima. A spacecraft launching from Earth toward Proxima Centauri must be aimed within an absurdly small angular tolerance. A targeting error of even 1/10,000th of a degree at launch becomes a billion-mile miss by the time the probe arrives. The spacecraft would sail past the target system, possibly never even close enough to take useful pictures. Targeting precision is just the beginning. The galaxy is moving. Our home star orbits the centre of the Milky Way at about 500,000 miles per hour. Proxima Centauri orbits the same centre at a slightly different speed, in a slightly different direction. Over the years a probe is in transit, the relative positions of the two stars shift. A spacecraft launched today aimed at the current position of Proxima would arrive at a position where Proxima used to be decades ago. The actual star would have moved. The probe would fly past empty space. To compensate, the launch trajectory has to lead the target. The spacecraft is aimed at where Proxima will be when the probe arrives, not where Proxima is now. Calculating that future position requires knowing both stars' velocities to extreme precision. Astronomers have been measuring stellar motions for centuries. Even with modern techniques, errors of a few percent in velocity measurements are still common. A few percent error in Proxima's velocity, multiplied by the decades of transit time, can mean the projected arrival point is off by millions of miles. The spacecraft needs the ability to correct its course in flight. Cruise phase engines, even small ones, can adjust the trajectory based on improving navigation data. Over years of flight, small adjustments accumulate into significant changes. The navigation problem is harder than it sounds. A spacecraft in interstellar space cannot simply ask Earth where to go. The signal delay is too long. By the time Earth receives a position request and sends back instructions, years have passed. The spacecraft has to navigate autonomously. Onboard navigation requires reference points. Ground-based spacecraft use radio beacons, GPS satellites, and tracking stations to know exactly where they are. None of these tools work at interstellar distances. The probe has to use the stars themselves as reference points. Star trackers on a spacecraft photograph the surrounding sky and compare the patterns to a stored star map. The relative positions of the stars reveal the spacecraft's location. The technique is called celestial navigation, and it has been used by sailors and astronomers for thousands of years in various forms. For an interstellar probe, the technique is more complex. As the spacecraft moves between stars, the parallax of nearby stars shifts. Stars close to the probe appear to move against the more distant background. By measuring those shifts precisely, the probe can determine its exact position in three-dimensional space. The math is intense. The required precision is at the limit of current sensor technology. The breakthrough Starshot team has identified onboard navigation as one of the major unsolved problems for the mission. Even if the navigation works perfectly, the probe needs power to push back against course errors. Small corrections require small thrusters and small fuel reserves. Bigger errors require bigger systems. Every additional pound of fuel for course corrections means additional pounds at launch. The energy budget for the entire mission may be the most punishing constraint of all. Push something heavy through space, fast, and you need a lot of energy. This sentence is the entire propulsion problem in summary. The actual numbers involved make the sentence much scarier. A spacecraft heading to Proxima Centauri at 5% of the speed of light needs to be accelerated to roughly 33 million miles per hour. Even for a modest spacecraft of 1 ton, the kinetic energy at that velocity is enormous. The energy equivalent of approximately 10 million tons of high explosives. For breakthrough Starshot, where the spacecraft is just a 1-gram chip, the energy required is much less. 1 gram at 20% of the speed of light needs energy equivalent to a few hundred pounds of high explosives. Either way, the energy has to come from somewhere. The Starshot laser array, the giant ground-based facility that would propel the chips, requires roughly 100 gigawatts of power output during the 10-minute push. 100 gigawatts equals about 100 billion watts. For comparison, an average household uses about 10,000 watts at peak. A large coal-fired power plant produces roughly 1 billion watts of electricity. The Starshot laser, during its 10-minute burn, would consume the equivalent of 100 large power plants, all firing at once. Most countries do not have 100 large power plants. The total electrical generating capacity of Australia in 2023 was about 65 gigawatts. The Starshot laser would require more electrical output than the entire continent. Of course, the laser only fires for 10 minutes per chip. The energy bill is finite. Modern engineering can store enormous amounts of energy in capacitors or batteries, then release it quickly during the launch window. The total energy consumed per launch is around 30 terawatt hours, the rough equivalent of 3 days of total electricity production for a country like Australia. For a single launch, that energy cost is staggering, but not impossible. The plan calls for thousands of launches. Tens of thousands. Each one requires the same energy budget. Building the infrastructure to support the campaign would consume a significant fraction of global energy production for years. For a crewed mission, the energy costs explode. A starship carrying even a small crew with shielding, life support, fuel and supplies for centuries weighs not a gram, but thousands of tons. The kinetic energy required to push such a ship to a fraction of light speed is correspondingly enormous. 1 million times Starshot's energy budget, many million times. No current technology can supply that energy. Even hypothetical fusion reactors at ideal performance levels could not provide enough power within reasonable mass budgets. Antimatter could, in principle, but only if humanity could produce antimatter in industrial quantities, which would itself require energy inputs beyond anything currently available. The energy problem is really a civilization problem. To launch a serious interstellar mission, humanity might need a power infrastructure orders of magnitude larger than what currently exists. Some thinkers, like physicist Freeman Dyson, have speculated about how civilizations could capture larger fractions of their host star's total energy output. A Dyson sphere or Dyson swarm surrounding a star to collect its full radiated power would provide more than enough energy for fleets of starships. Building such megastructures is far beyond current capability. The construction itself would require generations of engineering work. For now, the energy budget for any interstellar mission is unfeasible. Either the mission stays small, like Starshot, accepting a flyby with no possibility of stopping, or the mission stays imaginary, waiting for a future civilization with vastly greater capabilities. That gap between imagination and reality leads to the next problem. No government wants to fund what it cannot finish. Governments think in election cycles. Most run on 4-year or 5-year political terms. A few run on slightly longer planning horizons, maybe 20 or 30 years for major infrastructure projects. A serious interstellar mission requires planning horizons measured in centuries. This single fact has killed every ambitious Starship proposal. The math is unforgiving. A mission to Proxima Centauri at realistic speeds takes between 50 and 400 years one way. Add development time, construction time, and the time for data to come back, and the total project lifetime stretches across generations. No current political system has the structure to commit to a project that long. The Apollo program, which sent humans to the moon, took roughly 8 years from announcement to first landing. 8 years is short enough that the same political leadership could see the project through from start to finish. President John F. Kennedy committed to the moon in 1961. Astronauts walked on the surface in 1969. Multiple presidential administrations supported the effort, but the timeline fit comfortably within a single political generation. The Space Shuttle program ran from 1981 to 2011. 30 years. By the end, almost no one involved in the original design was still working on the program. Institutional knowledge had to be carefully preserved and transferred between generations of engineers. The International Space Station has been continuously inhabited since 2000, 25 years of continuous operation. Each component of the station was designed, built and launched by international partnerships that had to be renewed politically every few years. Sustaining the partnership has been a constant struggle, even with the relatively short timescales involved. A Starship project would face the same challenges, but multiplied across centuries. Imagine a Starship launched in 2050. The mission profile calls for a 100-year journey to Proxima, followed by decades of data transmission. The total project, from the start of detailed development through the end of useful science return, might span the years 2035 to 2200. 165 years. In 165 years, governments rise and fall, currencies are replaced, languages drift, ideologies shift. The country that funded the mission's launch might not exist by the time the data starts arriving. The funding agency that built the receiver array might be gone. The engineers who knew how to interpret the data signals might be dead, with their successors having lost the institutional knowledge. History shows how easily long-term projects fall apart. The construction of medieval cathedrals offers a partial counterexample. Major European cathedrals took multiple centuries to build. Construction began under one king and finished under a distant successor. The institutional structure of the Catholic Church provided continuity across the generations. Workers knew their grandchildren would finish what they had started. Modern democratic governments do not have that kind of institutional patience. Voters demand visible results. Elected officials want their names on completed projects. A Starship mission that could not promise results within a single political career would struggle to get funded at all. Private funding has been proposed as a solution. Yuri Milner's $100 million commitment to break through Starshot was a private gesture. The total budget for that program, if scaled up to actual launches, would run into the trillions of dollars. No single billionaire can write that check. International coalitions might provide stability, but international institutions rise and fall too. The League of Nations lasted 26 years. The European Union, in something like its current form, has lasted about 70. Counting on any human institution to remain functional and committed for centuries is a gamble against history. This is why interstellar travel might require something different from anything humanity has yet built. Add up everything in this mission briefing: the propulsion barriers, the radiation, the dust, the food, the water, the air, the genetic minimum, the psychological strain, the navigation precision, the energy budget, the political timeline, the destination's hostility, the planet's uncertain atmosphere, the star's flares, the tidal locking, the deceleration nightmare, the communication delay. Every one of those items has at least one solution that does not yet exist. For the propulsion alone, we need either fusion engines that run flawlessly for decades, antimatter production in industrial quantities, or laser arrays the size of small cities. None of these technologies is currently within reach. Best estimates suggest fusion propulsion might be available in 50 to 100 years if research continues at current pace. Antimatter manufacturing at meaningful scale is probably hundreds of years away, if ever. For the life support, we need closed ecosystems that can run for centuries with no resupply. Biosphere 2 failed at 2 years. Achieving a 400-year working closed system is an engineering challenge that has never been seriously attempted, and current efforts suggest we are decades away from even. The small-scale prototypes needed to start learning. For the radiation problem, we need shielding technologies that protect crews from cumulative cosmic ray exposure across decades. Current shielding adds prohibitive mass. Magnetic shielding requires power and durability that current superconductors cannot provide. Pharmaceutical and genetic protections are at very early stages of research. For the crew, we need a population large enough to remain genetically healthy and psychologically stable across multiple generations. The minimum size is at least several hundred people. Designing a habitat for that many crew members with all required life support and shielding gives a spacecraft mass measured in millions of tons. Accelerating that mass to a meaningful fraction of light speed using any known propulsion would require fuel quantities that are not just unavailable, but physically impossible with current technology. The honest mission planner adds these factors together and arrives at a brutal answer. A crewed mission to Proxima Centauri B, using only technology that currently exists, is impossible. Not difficult. Impossible. Using technology that might exist within 50 to 100 years, the mission becomes barely feasible, with low probability of success. The crew might launch. The crew might arrive. The crew probably will not return. The information they send home might or might not be useful. Using technology that might exist within 200 to 300 years, the mission becomes more plausible. Fusion engines might be reliable. Antimatter might be available in small quantities. Closed ecosystems might have been refined through centuries of experimentation on lunar bases and Mars colonies. The political infrastructure for a mission lasting centuries might have been built. For a mission to launch with reasonable confidence of success, the timeline pushes out further. Probably 400 years, possibly more, before all the necessary pieces are in place. That is an optimistic timeline. Pessimistic timelines suggest never. The energy requirements alone might exceed what humanity will ever generate. The biological problems might prove intractable. The political coordination might fail no matter how the technology evolves. Stephen Hawking, before his death in 2018, repeatedly warned that humanity needed to become a multi-planet species to survive. He was a strong supporter of breakthrough Starshot. Even Hawking acknowledged that his support was, in part, an act of hope, rather than a prediction of imminent success. Proxima Centauri B will still be there. The planet has been orbiting its star for billions of years. It will still be orbiting in another billion. The question is whether humanity, in any form, will still exist to make the trip. If the answer is yes, the trip will happen, eventually. The mission will succeed eventually. The first human will set foot on a world circling another star, eventually. If the answer is no, then Proxima will remain forever just out of reach. Visible. Calculated. Measured. And impossibly far. The mission briefing ends here. The decision to attempt the journey belongs to a generation that has not yet been born.